Very pleased to welcome you to the flagship seminar series organized by the Texas A&M Energy Institute. This is our English lecture series. Today, we're very pleased and honored to have Professor Paul Joskow of MIT to give a talk about the deep decarbonization of the electricity sector in 2050. So I'll let you read his illustrious bio on the flyer. But let me just say that Paul is the person when it comes to power system economics and deregulation. He, together with Dick Chilamanzi, published a book on markets for power, the analysis of electric utility deregulation in the year of 1983, when the world was still running everything in the electricity world the vertically integrated status. And he wrote the first book. And up until today, he's still playing a very influential role in a very recent MIT Futures of the Energy Storage report, where he, I believe, provide major intellectual input for the issue of the impact of energy storage on power systems. And of course, he has been the Elizabeth and James Killian Professor of Economics, and also the President Emeritus of the Alfred Sloan Foundation, and a long list of accolades and awards. But let's give the time to Professor Joskow and give Professor Joskow a big Texas-sized round of applause.
Thank you. And thank you and good morning. It's a pleasure for me to be here. I'm sorry I can't be with you in College Station. I've been there before, had a good time, maybe sometime in the future. So I'm going to talk today about decarbonizing the electric power sector and looking out roughly 30 years from now to 2050. The goal of this work is to look at what could be the attributes of efficient or least cost electric power sectors that achieve various CO2 emissions constraints in 2050. And this is joint work with a number of other colleagues, including Dick Chilamanzi and Derek Malaprabada, Hannes Pfeifenberger, and Howard Grunsbeck, and it comes out of the recently published study on the future of energy storage. I'll come back to that in a minute. So here we're going to look at different emission constraints going forward, including no mandated emissions limit. We look at 3 different regions of the US, including Texas. We look at a large set of generating and storage technologies that are available now or may be available in the future, how those costs may change down the road. We also look at likely changes in the wholesale market price distributions, so with different emissions constraints, system reliability considerations, and I'll have at the end just some policy observations, although I would say this is mostly a positive rather than a normative discussion of alternative futures. Whoops. Okay, for those of you who aren't familiar with electricity and electric power systems, here's a little picture. I'll be looking primarily at the generation component of electricity and how it's going to change. If we have time, I have some observations on transmission and also observations on pricing of electricity for ordinary retail customers going forward. And the major change that we'll be looking at is the introduction of non-fossil generating technologies, non-dispatchable generating technologies, wind, solar, storage, as well as dispatchable technologies such as nuclear power. And the idea here is really to see how these technologies could diffuse going forward by 2050 under a range of assumptions. So just as a reminder, the U.S. actually has quite a variable set of industrial organization. We have areas in the Northeast and in the Eastern Midwest, as well as in Texas, in ERCOT, the Electric Reliability Council of Texas, which have restructured. Generation is separated from distribution and transmission, and they're competitive markets at the wholesale level. And in many of these regions, there's also competition at the retail level. Then there are areas like California, where they've separated generation from transmission and distribution, but there is no meaningful retail competition there. And then there are large regions in the West, and especially in the Southeast, which are pretty much the way they were 20 years ago, with extensive vertical integration and regulation. The introduction of independent power producers that sell to incumbent utilities that are seeking to meet their obligations to their customers. So the U.S. electric power sector, despite what you sometimes read, is really quite diverse, and that's true in Canada, which is physically integrated with the United States electrically. Alberta has a system that's a little bit like the system in ERCOT. There's an independent system operator in Ontario, but the generation component is highly concentrated and still partially regulated. And just since I'm speaking to you in Texas, this is a picture of ERCOT. And the one observation I'll make, and ERCOT covers about 90% of Texas. It is the model restructured, deregulated market with a few minor exceptions. And I think what distinguishes it is it's basically barely connected to the rest of the United States. If we have time at the end, I'll come back and discuss some of the transmission and market integration issues. But I know, especially during the blackouts in Texas in February of 2021, there were questions about whether transmission should be expanded and the market integrated with neighboring areas in the north and the east. But in that sense, it's unique. I mean, compared to California, which has not quite as large a peak load, but has extensive interconnections with the rest of the United States, Texas is fairly isolated. On the retail competition front, again, there's a lot of diversity, but overall, there are relatively few states that have meaningful retail competition. That is where the incumbent distribution company provides delivery services, and individual customers can arrange for their own supplies of energy services. And it's primarily in the Northeast and Texas. The lines here that are hatched, they say partial. Well, it's really partial in these states. And it really is only about a dozen states where there's meaningful retail competition at the present time. And in the other states, power supply arrangements are made by the incumbent transmission and distribution companies, referred to as load-serving entities, and they do that with a combination of generation they own and or buy, subject to primarily to state commission regulation. So what kinds of challenges are there going to be as we move to a deeply decarbonized system? Well, first of all, a deeply decarbonized system is going to have a large fraction of the generation portfolio will be made up of wind and solar generation. And intermittency is a challenge. We'll be migrating from a system which is built on dispatchable generation, that is where a system operator or a market organizer stacks up the generators according to the lowest to the highest bids, and demand varies, and the dispatcher turns on and off the generators to balance supply and demand as demand varies over the day. In a system dominated by wind and solar, on the other hand, the generation from these resources is driven by the wind and solar irradiation, and those are not under the control of the system operator or the market operator, but rather are exogenous to those to exogenous to those decisions of dispatch. And this is a kind of a major challenge. It's a challenge for maintaining reliability. And by reliability here, I mean both the balancing supply and demand with very low probabilities of involuntary curtailments or blackouts, but also maintaining the physical attributes of electric power networks, what economists think of as the plumbing that can be ignored, frequency, voltage, reactive power, the inertia to maintain voltage, operating reserves to deal with the rapid fluctuations in supply and demand. Intermittency creates new reliability issues. And it's not just intermittency. It's the fact that when the wind blows in a particular region, it affects all the generators, not just one generator that might have an outage for some reason. And at night, there's no generation from solar generators because it's dark. And this correlation in output across many generators is pretty new to the system and creates some significant reliability requirements. And then finally, a challenge is to achieve an efficient portfolio of wind, solar, hydro, nuclear, and other low or no carbon generating technologies and storage. We really have to investigate the investment incentives and financing for these technologies, whether and how to expand the transmission network. There are distribution network issues, especially as rooftop solar expands and distributed generation expands and distributed storage expands. And a question I'm not going to deal with today is how we get from here to there if we actually have the normative goal of reaching a deeply decarbonized system. We're going to be looking at what it would look like if we just assume it's an optimal system. So just talking about intermittency, this is just for the last roughly 2 years, the production of wind generators in ERCOT and covering most of Texas. As you can see, there are very large daily variations in the amount of wind produced. If you look really with a hard eye, you'll see there's less in the summer than there is in the winter, at least on average, quite a bit less here. And that's just something one has to deal with in a system with intermittency because the wind varies from not just from day to day, but from hour to hour and minute to minute. And here's a picture again for ERCOT. I just picked an arbitrary day in the middle of December. This is the demand on the system, or the load, which has a kind of, that's the evening, that's the early morning, it goes up during the day and then comes down at night. And this is the wind generation on that day, which kind of does its own thing. And it's up in the middle of the day, then down over here, and then up at night, and following the wind sources. And there are fairly significant seasonal differences. So here's a summer day, and it looks kind of the same as the other day, except this is where you have to learn how to lie with statistics. You really have to look at the horizontal axis, and you can see the wind generation on this summer day is really quite low, and it goes down in the middle of the day as demand is going up. And this is kind of the challenge of intermittency, because we need balancing resources, either generation resources that can be dispatched or storage to balance supply and demand, and in some cases quite quickly. And this is just an entire year in ERCOT. The red are the capacity factors of the solar generators. The blue are the capacity factors of the wind generators. And the primary point is to show there's a lot of variation in how often they run. And I'll just point out that there are periods of time where they both run very little. And this is the kind of long duration event that is particularly challenging in a system dominated by wind and solar generation. And just to change states, this is for California, for the California ISO, wind and solar generation, along with the day ahead wholesale prices. And you can see these are the solar, and not surprisingly, it goes up during the day and it goes to zero at night. You can see that there's some regularity to it, but all the days aren't the same. Here are some days when it must have been cloudy or raining. You can get some rapid changes in supplies during the day that have to be balanced by the system. Here, the green is the wind generation, and at least during this period of time, which is the fall of 2022, the wind is being kind of helpful. The wind tends to blow at night when the sun's not shining, and less so during the day when the sun is shining, so that those two resources are negatively correlated. But you can also see that there's a dramatic effect on the price distributions, even here, where there still is a lot of thermal generation that's dispatchable. You can see the prices get really low in the middle of the day when the sun is shining. And then as the sun goes down, prices shoot up rather significantly, and the prices are on this axis. And these are all a consequence of intermittency and the variable relationships between different types of intermittent generators in terms of their supply opportunities. And this is a picture for California, for the California ISO on 2 days when they had rolling blackouts. And I just want to point out two things. The blue lines are the actual demand on the system operator. The orange line is the net demand, they call the net demand in California, which is net of the wind and solar production. And the two things I'd like to point out is that the net demand peaks at a different time from the gross demand. And this means the challenge for the system operator is not meeting that demand. At least for now, there's plenty of solar in the system to meet that demand. It's meeting the net demand, and the net demand peaks at a different time from the gross demand. And in fact, that's when the outages were, not during the peak period, but during the peak period of the net demand. These gray lines are where the rolling blackouts were ordered by the ISO. This has implications for how one plans for reliability going forward, and how one models both the gross demand but also the net demand on the system. The second thing I'll point out is, because this is a solar-dominated system for now, there's a very high ramp, that is, increase in supply that has to be provided by some dispatchable resources, or maybe by chance by the wind, to accommodate the reduction in supply from the sun going down. And that's a rapid ramp. It's not smooth. Some people characterize it not by the distance, by the number of megawatts, but by the mileage, including the up and down. And that has implications for maintaining the reliability of the system. And on this day, August 15th, you can see that the net demand, the ramp didn't even go in a linear fashion. And that's because the wind came up for a short period of time and helped to meet demand. Okay, so let me talk about the approach we've taken. And as I indicated, this is joint work with my MIT colleagues and students. It's primarily drawn from Chapter 6 and Chapter 8 in the MIT Future of Storage study, and some more recent work that we've been doing on retail rate design with other colleagues. Dick Schmalensky and I are still working together after all these years. Not only we write a book together published in 1983, but we taught together beginning in 1977. Although we're getting a little long in the tooth, so we need to bring in some younger people to help us. And we did in this case. We rely on an optimal capacity expansion model, an open source model called GenX, really to run what I think of as experiments with a wide range of carbon constraints, generating technologies, storage technologies, and associated cost and performance assumptions for 2050. And we chose 2050 because we wanted to go far enough out that we could assume that a lot of the existing capacity would be retired by then. This model's also been used to look at transition work. Jesse Jenkins, who used to be at MIT and is now at Princeton, has used this model to look at the transitions from here to there, and it's complementary to the work we've done. We look at 3 regions: the Northeast, the Southeast, and Texas. And I just want to remind people, this is only a model. We're not making forecasts. We're not making normative statements about what should be done and shouldn't be done. We're using this to run experiments, really to see what matters and what doesn't matter that much. For this discussion today, I'm not going to focus on the storage attributes of that work, much of which was done by engineers at MIT, but on the general attributes of optimal or least cost systems under a variety of assumptions. So these are the three regions. The Northeast is New York plus New England. That's 2 ISOs. Texas is primarily ERCOT. And the Southeast is an amalgam of utilities, including the Southern Company, the utilities in Florida, including Florida Power and Light, and the Tennessee Valley Authority, which is up here. And what distinguishes these regions, and the reason we've chosen them is we've also done some other regions as well, is these regions at the present time vary in their carbon intensity. So you can see the Northeast is the lowest and Texas is the highest, with the Southeast in between. But more importantly, from our perspective, they vary in the opportunities to adopt and the costs of adopting wind, solar, and solar technologies. So the Northeast, we don't have a lot of great solar or wind resources. If you've been here in the winter, it gets dark at about 4 o'clock. And we don't have large flat areas that are conducive to building efficient solar and wind farms. Actually, for that reason, much of the development is now being pushed offshore by policymakers. The Southeast has much better solar resources, maybe not as good wind resources, but it's also has a lot of nuclear power. And one of the things we look at is the benefits and costs of extending the lives of the existing nuclear plants. And then finally, ERCOT, or Texas, has fantastic wind and solar resources, and making it the cost, at least in anticipation, the costs being much lower than in the Southeast. What we're going to look at are different CO2 emissions. We're going to assume there are constraints, as well as looking at what the system would do without any regulatory constraints at all. We also include increases in electricity demand to reflect electrification of other sectors, in particular transportation, buildings, and some other sectors. And we embody assumptions about continual reduction in the costs of wind and solar and lithium-ion storage, which is by far the predominant form of storage going in today. We make some different assumptions in the Southeast and Northeast about incumbent generation. In the Southeast, we look at retaining existing nuclear. In the Northeast, it's retaining existing hydro. And as you will see, for I think pretty good reasons, we continue in what we think of as being the most interesting cases, continue to rely on some natural gas generation, which turns out to be very valuable as you get closer and closer to zero emissions. So we look at a range of available technologies, wind and solar PV at the grid level, various storage technologies. The dominant technology, legacy technology in the US, is actually pumped storage, where they pump water up on a hill at night and you dump it down during the day. We've got 2 of those in New England. Stored hydro can also be, conventional hydro can be used in that way, but it's pretty hard to build those types of facilities today for public acceptance reasons and environmental reasons. And almost all of the storage being installed today are lithium-ion battery technology. But we also look at potential future technologies, so-called long-duration storage. I'll come back and talk what that even means. Storage technologies can be dispatched, so they're dispatchable, but they have limited energy supplies. As I indicated, we look at nuclear. incumbent nuclear in the southeast, the incumbent hydro in the northeast. We allow for gas with CCS to be introduced in a least cost portfolio. We have some analysis of hydrogen production and use. I'm not going to talk about that today. And then some other low or no carbon generating technologies that are in principle dispatchable. And we do some work on demand response, demand shifting within particular days, something that's quite feasible as electric vehicles expand. I won't go into the details of the model, but it's an optimization model that does a lot of back and forth. We have pretty good temporal resolution, certainly on the supply side, hourly data for 7 years. On the demand side, the temporal resolution is not nearly as good. And I would say one of the appropriate criticisms of this analysis is we're not picking up some of the extreme weather events that we've seen in the last couple of years. I think I've already so on the reliability side, we actually do build in reliability considerations into the model to actually get the model to achieve what we consider to be reasonable reliability attributes, that is hours and amounts of lost load. We have to assume a value of lost load of $50,000 a megawatt hour. And just to compare that with what's used in ERCOT today, which has the most visible application of the value of lost load in its market, that was $9,000 for a few years. I believe it was recently reduced to $6,000 as the highest value. So there's a significant reliability constraint that we've had to put onto the model to build enough generation and storage to balance supply and demand in a way that meets current reliability criteria. Again, as I indicated, we build in substantial increase in electricity demand, and we make crude assumptions about transmission, a topic that I've been looking at separately. Okay, so one thing I would say that's actually pretty important is the costs of grid scale PV, wind, and batteries has declined over time rather dramatically, and I would say unexpectedly. And there are different ways of measuring the cost. This is one way that Lawrence Berkeley National Lab uses, but as you can see, these costs have gone down over time. This is for residential and commercial PV, rooftop PV. They've come down significantly over time. This is for wind turbines. Those costs have come down significantly over time. And more importantly, the quality, in a sense, has increased. They're much higher. They have higher capacity factors, and they can be put offshore if the water is shallow enough, and take advantage of more sustained winds than is the case with smaller onshore wind turbines, especially in the Northeast, where the onshore wind resource is not nearly as good. And then lithium battery pack costs have also declined rather significantly, driven by electric vehicles so far. And it's important for people listening to understand, if we've built in continuing cost reductions over time based on studies that NREL, the National Renewable Energy Laboratory, has done going to 2050, and that's pretty important. Okay, so here is a simulation. This is kind of our base case run of this modeling exercise. And let me just run you through here what's going on here. Texas, the Southeast, and the Northeast. Then we have different carbon constraints, no limit. I kind of insisted on this. Why don't we look at what the system is going to look like before we start putting regulations on it? Then there's 10 grams per kilowatt hour, 5 grams. 5 grams is 95 to 98% carbon free. And we also initially did some cases with 0, that is purely carbon free, no carbon emitted at all. And the costs of going from 5 to 0 are very, very high. And we decided that it's not worth looking at. It's just too high, and the carbon emissions reductions you get are too significant. And we didn't want to be fooled by the attributes of that system, since since the marginal costs of reducing a ton of carbon dioxide from 1% to 0% is thousands of dollars in the Northeast. We're just assuming something else is going to have to come along, or we're just not going to go to zero. And this is consistent with what a number of others are finding. So if we just look here at no limit, you see significant differences between the regions. So this is Texas. Texas, because its solar and wind resources are so good, actually without anyone from Washington coming in and saying you've got to reduce your emissions, just by pure economics, you reduce your emissions a lot. And there's a lot of wind as there is now. There's quite a bit of solar, and solar is coming in pretty quickly in Texas. There's some storage, but there's also gas generation. And this is CCGT generation under no limits case. And the CCGTs not only provide energy, they're also like long duration storage, because you can run them. You want to run them for 2 hours, you can do that. You want to run them for 10 hours, you can do that. You want to run them for 20 hours, you can do that. Then the Southeast, which has very good solar resources, which is yellow, but not such hot wind resources, you get a significant reduction in CO2 emissions, but not nearly as much as in Texas, and a lot of reliance without any constraints on combined cycle using gas. And then the Northeast, which basically has terrible wind and solar resources on its own, the offshore wind costs are, I think the lowest is about $79, but that contract's already been breached. In New Jersey, they've gone over $100 a megawatt hour. So that's pretty expensive. It's not the 3.5 cents that some people talk about. And then we start putting on constraints. And here's a 10-gram constraint. And what happens when you put on constraints is you switch from regular CCGTs to CCGTs with carbon capture and storage to produce roughly 90% less CO2 emissions per megawatt hour. You get more wind and you get more solar if you look at the Southeast, also in Texas, and also in the Northeast when you push it. And then as you go down to 5 grams, you can see the same kind of effect with more wind and solar, more storage in the Southeast. The dark blue is nuclear, existing nuclear that stays in the system. In fact, it's probably the cheapest decarbonization technology of all. And this is zero. I'm not going to talk very much about that here. If we look over here, these are the average system costs in different scenarios. And you can see as you tighten the carbon emissions constraints, the costs go up. And people have looked at this and said, well, the costs don't go up that much. Well, what's that much? Let's just look at New England. That's about 38. And if we went to 5, that's about 52. That's 14. I think that's pretty big myself. That's about a 25% increase. Whereas in Texas and the Southeast, we get a smaller increase, but we still get an increase, and we get very significant increases if we really go to zero. And I think that's an important lesson that we really hadn't understood. It's just a significant change to go really to zero on the system. And you can back out for yourself the marginal cost of going from here to there is really quite high. And finally, we look at curtailments. One of the attributes of systems with a lot of intermittent generation is you get times where you have very robust wind and very robust sun, and you're producing too much energy to meet demand. So you've got to have curtailments in some way. And as you can see, as you tighten these emissions constraints, you've got to build more and more of the wind and solar, and you get more and more curtailments on the system. We're already seeing that today. And if you go all the way to zero, you get a lot of curtailments on the system because you're basically overbuilding in a non-pejorative sense to take account of the days when you have low wind and solar. You build a lot of capacity, but that means on days when the wind and the solar are robust, you get you have too much generation. You've got to turn it off somehow. This is the same thing. I've just focused on 5 and no limit to get a better picture of what's going on here and what I just said, and you also get a better picture for what the cost changes are. And I don't think they're trivial. And I guess it depends in your mind. What do you mean by large? But they're certainly not zero, as some people have suggested. Though changes in federal policy with regard to tax credits for most of these technologies and the Inflation Reduction Act will certainly mute the cost effects of making these changes. We look at cost sensitivities. We don't actually model the Inflation Reduction Act because it was passed after we did this, but we do look at high, medium, and low cases for VRE generation and for lithium-ion batteries, and you kind of get what you would expect in this case. In a no limits case, you're going to get more wind and hydro. In the limits case, you get an effect on cost, which is rather significant. When the technologies are cheaper, the costs are lower. And at the 5 gram case, that is true as well. And there's some implications for storage, but I'm not going to go into those here. There are lots of questions of nuclear, and I've been studying nuclear power since before I started to work on our book on markets for power. And nuclear power has improved dramatically in the United States over time, at least in terms of operating attributes. The average capacity factor last year in the U.S. was over 90%. The plants are built. Many of them were expensive to build, but they're now built. Investments continue to be made to meet safety and performance requirements. But we do look at the Southeast, which we think is the most likely region for both cost, the regulatory framework there, and public acceptance for nuclear to have the opportunity to continue to operate into 2050 and beyond. And we find that nuclear is chosen to continue operating, and it has significant impacts on costs, and it displaces the need for storage and the need for in the Southeast, and the need for wind by providing a dispatchable round-the-clock resource. So I think probably too little attention has been given to retaining the nuclear plants we have today. Our model won't pick new nuclear plants because they're too expensive. We use the latest cost numbers for the plants being built in the U.S. and Finland and France and in England, and they're just too expensive. There is a hope that nuclear will become less expensive going forward with small modular, more factory-based technologies, but that's yet to be seen. And in my lifetime, people are always let's put it this way: no one's ever overestimated the cost of a nuclear power plant. So we'll have to see what happens. We also look at intraday demand shifting based on some NREL analysis, and there's a significant potential cost saving and saving in storage from intraday shifting to basically shift peak loads and smooth them out during the day when prices are high. And basically, not surprisingly, if a lot of this is basically shifting the loads for electric cars, they are batteries. They provide a substitute for storage, and that's what you're seeing here in Texas and the Northeast when we look at demand flexibility. And this is an area where a lot more work could be done. Let me just say a word about storage. Storage has a lot of attributes that affect cost and performance. I'll just look at 2 here. One is the power, that is, how many kilowatts can it produce? And the other is the energy, how many kilowatt hours can it produce? Lithium-ion batteries are here. This is the range of cost assumptions. We primarily use one in the middle rather than the low or the high. Lithium-ion batteries have relatively low costs of power, but relatively high costs of energy. for the typical lithium-ion battery, let's say it's 6 kilowatts, it is going to have somewhere between 12 and 24 kilowatt hours. The new technologies, what are often called long-duration technologies, have high costs of power but low costs of energy, so that you can, for any capacity, let's say it's 100 megawatts, you can put a lot of megawatt hours in there so it can run for a long period of time. These technologies are mostly experimental today, but they may be important in the future, especially to deal with extended severe weather events. And one of the things we found, which I think needs to be explored more, is that long duration storage, that is, these new technologies, can reduce costs, but they reduce them a lot, only in the zero case, which we argue you probably shouldn't be looking at anyway. They reduce costs modestly in the other cases. I think we're going to find that when we really look at the reliability side, that some of these technologies are important for maintaining reliability under certain conditions, and to maintain that reliability is going to be fairly expensive. Okay, let me now turn finally to how this affects competitive wholesale markets. So this is a depiction of a competitive wholesale market. Basically, they're a mix of generators, nuclear and coal and CCGT and conventional gas and peakers. They bid into the market, and there's a bid-based economic dispatch curve that emerges that's pretty stable over from day to day, putting aside downtime for maintenance and so on. The bid-based dispatch curve is fairly stable, and the market operates by moving up and down the dispatch curve as demand moves up and down during the day and so on. And this is quite analogous to the old way we did it with an economic dispatch curve based on the marginal costs of running different generators in a portfolio, except here that it's bid-based. In a system dominated with renewables that are intermittent, wind and solar, it doesn't look like that at all. One of the attributes that's important of wind and solar technology is they're expensive to build, but the marginal cost of running them once they're built is close to zero. So you're going to have a lot of periods when the dispatch curve is really close to the zero line. Then there are going to be periods when storage is operating, buying and selling, and that's going to raise prices somewhat. And then there are going to be periods when demand is high and it's more economical to shed demand, hopefully not involuntarily, with very high prices than it is to build additional capacity. Moreover, because of intermittency, the stability that we find in traditional dispatch curves disappears. As the wind and the sun moves around, this dispatch curve moves back and forth like that. And the price distribution is going to therefore have a lot of zeros or close to zeros, some intermediate numbers, and some very high numbers as prices rise to clear the market up to the value of lost load. In our case, they can be as high as $50,000 a megawatt hour. And we see that these are the actual outputs of the model, where our closest thing to a spot energy price is produced, which has some of the attributes of the ERCOT market. We're not simulating the market, but it's the best one to compare it to because it doesn't have capacity payments like New England does, where its capacity payments are 30 or 40% of total wholesale market revenues. And you can see as you move towards, let's say, 5 grams, 98% carbon free, the number of hours when prices are really low go up rather significantly. And the number of hours when prices are really high also go up rather significantly. So the distribution becomes one with a lower tail, with a lot of density of very, very low prices, and an upper tail with much more density than we see today of very, very high prices. And as you go closer to zero, this effect just increases. And if you look at the different technologies and ask the question, well, how much of their revenue is coming from hours when prices are really very high or very low. For CCGTs, this is a lot of their revenues coming when prices are very high. And for open cycle, a little of those are installed. In some cases, the prices, that's all, they depend entirely on very, very high prices, over $1,000 a megawatt hour. And for others, the revenues to satisfy a break-even constraint. I mean, nobody makes extra money here. This is entry is all the costs, capital and operating costs have to be covered. It also involves a large number of high-priced hours, and in most markets in the U.S. anyway, but also in Europe, these constrained conditions, when you're up against a supply constraint, when these markets work the worst, either because of government actions to put in price caps, or because of system operator actions to take things outside of the dispatch curve to maintain reliability, or due to other changes in the system that don't allow prices to be achieved, and that could include not having adequate demand response in the system to clear the market. So we have a number of other analyses. We look at how storage affects these results, and the answer is not much. But there are some implications, and I'll close with this. These systems, if we go to deeply decarbonized systems dominated by wind, solar, and storage, we're going to have a lot more price volatility. And we're going to depend, from an investment perspective, on getting revenues from these high-priced hours. As a result, regulatory price caps and out-of-market dispatch that presently exist are going to further distort investment incentives and create reliability problems. It complicates reliability analysis because it's got to reflect the stochastic properties of VRE generation. And changing price distributions not only affect wholesale prices, but they strengthen the case for changing the way we price electricity for residential and most commercial customers, which are basically flat rates that don't vary by time of day, that don't respond to critical peak periods. And it reinvigorates, I think, the interest in looking at dynamic prices at the retail levels, at time of use prices, at critical peak pricing programs, and at load control programs. And we always focus on the wholesale market, but there's a tendency to forget that in the end, the signals have to be conveyed to retail customers. And right now, despite the fact that we have over 100 million smart meters have been installed in the US, something like 90% of the residential and commercial customers are still on flat rates, which maybe vary by season, but don't vary from hour to hour or from day to day. Let me just, I should close. There's a lot of things we didn't do in this analysis so far. We didn't look at what the best mechanism to get from here to there. We just told you what there would look like if we had a good mechanism. We didn't model the transitions, although others have using the same model. We don't have a granular model of transmission. We've done some other work on transmission issues, which I think are significant. The demand side modeling is fairly crude. We haven't looked at the subsidies and recent federal regulation. We haven't taken account of prices going negative. And our prices can go to zero, but they can't go negative. But we've seen negative prices already. And this is due to subsidies, production tax credits, which make it of interest to wind and solar generators that have production tax credits to operate, even at prices below zero, because they get paid $25 a megawatt hour or so. There's network congestion that makes it impossible to run the generators when their supply is very high. And a lot of long-term contracts are being used to support investment in wind and solar, and they're kind of poorly designed to deal with these curtailment situations. And negative prices can create some other distortions in the system that we haven't looked at but require more attention. And just to give you a final example, this is California again, which is a dominant solar system. And you can see the frequency of negative prices as this is a summer summer month, July, when California peaks and the solar radiation peaks, you can see over time the number of negative priced hours is going up, and that's because there's often too much solar to be accommodated by the system, not so much for the reasons we have in our modeling, which is you just get too much supply, but because of constraints on the transmission network, local constraints, suggesting again that understanding the network implications at both the transmission and distribution levels of a deeply decarbonized system are very, very important going forward. And why don't I stop there? Thank you.